Okay.
Okay, welcome everyone. It is my pleasure to introduce our seminar today. And the seminar speaker is Luca Ballotta from Delft University. Now, before telling you about Luca's history, let me just mention that this seminar is organized within the framework of the CDC, Road to CDC initiative. You know that there will be CDC in Milan in a couple of months. And this initiative of the IEEE-CSS Italy chapter was to have a series of seminars, and one of which that we're hosting today, it's by Luca Ballotta. The first time I met Luca was a few years ago during a summer school in Bertinoro. He was a PhD student in Padova.
Great summer school.
It was yeah, it was when Italy won the Euro Cup. So
Yeah,
that's it started with that, at least. And I know that Luca then spent quite some time as visiting student in Leeds at MIT.
Mm-hmm. Yeah.
And he eventually graduated from Padua and then joined Delft University. And now it's our pleasure to host him for his seminar today. And please, Luca, I think you can switch the slides.
Thank you. So let me... So let's see if this gets any better. Oh. Oh, Giacomo, how do I switch slides here on the...
Devi cambiare la condivisione.
Grazie. Allora, aspetta, vai pure su... Per questo sto condividendo. Allora, ricomincio. Sì. Allora, questo chiuso. E poi l'Adobe lo condivido.
Sì.
Ok.
Questo mi sembra che ha risolto i nostri problemi. No.
Non so, vuoi provare a cambiare l'adattatore? Non so se posso cambiare qualcosa in realtà o se sia più il capo. No, perché poi i problemi sono un po'...
Non sono nelle risoluzioni.
This is more stable.
Okay.
Okay.
Technical problem sorted.
We made it.
Please look up.
Thank you. Thank you, Giacomo, for introducing, and thanks everybody for attending. So in this talk, I want to give you an overview of some research I've been doing through my PhD and also more recently about distributed control, and in particular the effects that communication delays have on distributed control. I'm not sure what background in distributed controller specifically you have, so I'll try to be a bit generic at the beginning. If you have any questions, of course, just jump in and ask at any time. And you may also tell me if you feel I might actually go faster in some cases. So to give some motivation, Here it is. Okay, yes, thanks. Okay, perfect. So just to give you some motivation, in a sense, here I'll be mostly motivating from network control systems and large scale systems where you have a lot of interconnected devices that communicate over some wireless medium usually. So that will be essentially the main motivation for communication delays, as well as I'll make clear in a few slides. So these are just a few applications on large scale, especially distributed systems where you might want to implement some distributed control strategies so that the devices communicate and together somehow achieve some control goal in a coordinated or collaborative way. So just to clarify what I mean by quantifying the performance of the controller, here you see what you typically see in, let's say, what is typically assumed in the literature when you want to allocate some resources. And if you have some performance cost that you want to minimize, that you see on the y-axis, usually this is one tries to allocate as many resources as possible in order to decrease the cost. And then, of course, for a given amount of resources, you may also be able to optimize specifically for the, for example, control architecture or control gains that you're using. But this is the typical assumption. But in many cases, this actually spawns from intuition, let's say, in heuristics reasoning, rather than more precise quantification. So just to make it clear, imagine you have a large-scale system with a lot of sensor actuators. You may deploy more, less or fewer communication links. And let's say, intuitive assumption is that if you want to increase the performance of the controller, you need to deploy a lot of communication links. So communication is faster, information is exchanged in a more timely way, and this helps, let's say, stabilization, for example, to some point. But this is somehow heuristic in a sense. This is usually assumed, but it's at least we found it difficult to find systematic studies where you could quantify performance in a very precise way and showing that, for example, an all-to-all communication topology is the best, for example. So in such a scenario, do we need to use all communication links, for example, between any pair of devices? And this kind of questions were we let's say asked ourselves this kind of questions that was back a few years back at the beginning of my PhD, more or less. And we've done some work towards these directions, towards this more deeper understanding. So I would like to let's say give you some ideas of what we let's say some answers we try to give to this kind of questions. So specifically, considering communication delays, how do communication delays shape the optimal controller? So we're not interested in just any, let's say, controller. So for example, stabilizing a system, but also getting high performance. So for example, high fast convergence speed, for example. And I'll divide this talk into two parts. I'll try to be, let's say, light in terms of formalism, but of course, I'll be happy to go deeper if you just want to ask any question. So the first part will be studying a performance trade-off between centralized controllers. So centralized in the context of network and distributed control for us, in this case, means all-to-all communication. So very dense interconnections versus decentralized or more broadly sparse controller architectures. So we'll just deploy a few strategic links, but the overall network topology is a sparse graph. So now I'll be analyzing the, let's say, performance you get in these two scenarios. And a very interesting performance trade-off arises here. I'll show you later, The second part will be a bit more towards a related kind of system, which is, these are usually called in the literature spatially invariant systems, and they are, let's say, a model for yet either distributed parameter systems or even an abstraction for multi-agent system network systems, where you have some spatial symmetry with respect to the dynamics. I'll make this clear in a while. So let me start with the first part, and actually let me first thank my collaborators, Luca, Hunkal, Mihailo, and Vijay. So this first part connects to what I mentioned at the beginning. So usually when you want to choose a controller, and specifically a controller architecture, one typically tries to trade off between performance and the complexity that affects how feasible, how costly the implementation is. And this usually, or at least it's assumed, directly relates to the number of interconnections, for example. So a very dense communication topology is usually regarded as very, let's say, as difficult to implement or to maintain, to scale. So it has some scalability issues, let's say, in practice. So one typically tries to find a balance between these two, where on the one hand, centralized controller, so all-to-all communication network, gives you a high performance, and sparse distributed controllers are better in terms of practical, let's say, implementation, practical costs. However, is this always the case? So as I argued at the beginning, sometimes this is very, let's say, heuristic. And so to, let's say, find, we wanted to look for, let's say, we wanted to challenge this assumption. So we formulated this problem, let's say the problem of finding the optimal controller for multi-agent network system. And we posed this assumption that the communication delays, so the amount of time information takes to travel, let's say, from any node in the network to any other node in the network through a direct link, the amount of this delay increases with the number of communication links. And this actually relates to some, let's say, practical implementations. For example, when you have shared bandwidth, if you have a lot of links, each link gets a smaller piece of the cake, so the bandwidth. So that might increase the delays, let's say, with some, of course, these are, let's say, simplifying assumption, but it's not that far from reality. And even if you have time-slotted protocols, for example, you can imagine if you have two neighbors, then you only need 2 communication rounds to get to average, for example, all the information. If you have 50 neighbors, then you'll need a lot of time to get information and to exchange information with each of them. So this is just to visualize this. If you have only 2 links for each robot, you have this entails small delays. If you have double the links, you have, say, double the delay or whatever, bigger delays. And after this assumption, you actually get that in general, the optimal controller architecture is not centralized, not densely sparse. And you see it here. So here, just to visualize this, you see, take this as a reference. If you have on the x-axis, let's say, number of links, so that quantifies how dense the network is. The total cost that I'll make more precise in a few slides, but the total cost that quantifies performance of your controller is minimized, let's say, with 2 links for each robot. And it's actually given, you can sort of study that both numerically and in some very specific cases analytically. The total cost curve is given by a decreasing term, which is, let's say, how good you're doing when you add links. And you're doing, to some extent, you're doing better because you are making information exchange faster. So on the one hand, you are increasing performance, so you're decreasing the cost if you deploy more links. But on the other hand, after that assumption, if you increase the links, you have this increasing curve, which accounts for the fact that somehow feedback information, the quality of the feedback information is degrades if you have longer delays. So you don't really want the information to be too old, otherwise it's basically useless. And that is what this increasing curve is saying. So you see that, for example, with this architecture, with just, let's say, one pair of neighbors, you are at this point. So very small latency costs, quite large network, let's say, cost. If you have this architecture, you increase the latency cost, you decrease the network cost, and this actually gets you to the optimal cost that you can get, and so on and so forth. Now, I don't want to go too much in detail here, but just to give a sense of the setup we're considering here, the control task we consider was consensus in mean square. So consensus on a stochastic dynamics. And so we consider symmetric feedback gains. And so the for each architecture, you have a matrix K, which is a symmetric matrix of gains that you want to minimize. So for each given architecture, you're given a certain structure on the matrix K, and you can find optimal. You want to find optimal gains so as to essentially imagine this is a consensus task. So you want to minimize. You want to drive X as close to 0 as possible, and you want to minimize the steady state variance of the process X under some Brownian noise, whatever. This is how it looks on if you have 4 interconnections. And well, I'll go quick on this. This is actually not that important, but this is just to show you that there's a way under continuous time single integrator dynamics to exactly compute this cost. This is quite classic, very interesting, actually, mathematical literature. Maybe it's actually possible you know it better than I do. But so you have this kind of curves, which are actually strictly convex. So it means that for this simple case, we can compute at least numerically, the optimal controller, because it just amounts to solving a convex problem. And so that is the problem we want to solve. You can rephrase it this way, where these sigmas are computed in closed form. So the problem is nice, it's convex in this case, and it's quite easy to solve. And we also, just for comparison, studied this approximation, which is even for more, let's say, challenging dynamics, it is always convex, and actually you can solve it in closed form. It's very easy. And so this is, and numerical results. So this is what I was saying. If you have constant delays, so if the delays doesn't change with the architecture, then the costs are all decreasing. And this is quite intuitive because if you allow information to be shared more, let's say, faster across the network, then you can stabilize your system better. But as soon as the delays increase with the communication, with the links. So for example, their delays are directly proportional to the number of links in the network. Here they grow with the squared root of the interconnections. You see that you have these U-shaped curves, which means that the optimal architecture is not the all-to-all graph. So it's not super dense network, but it's quite sparse. So there it's very sparse. Here it's, in this case, is still quite sparse. So this not only means that you're gaining, let's say, in terms of, let's say, complexity of your controller or feasibility of costs of bandwidth, but you're also gaining in terms of control performance, which is, let's say, not trivial a priori, but under the assumptions, this is the case. The same thing actually can be numerically seen also for other dynamics. So down integrators, discrete time dynamics. And you have the same behavior. And also for general undirected network, one nice thing is that for any undirected network, if the matrix K is symmetric, then the problem is still convex, at least for the continuous time dynamics and the single integrator dynamics, still convex. So we can say that numerically, this is actually the correct solution to the problem. And this is how, just to make an example, the optimal topology looks like in this case. So not only connecting the neighbors, but also the neighbors of neighbors, and then that's it. You don't need to go further away. You're already at the optimum, essentially, at least for this example. And the same thing actually can be observed also for deterministic consensus dynamics, where you want to maximize convergence speed. So rather than before the dynamics was stochastic, so the typical problem is minimizing the steady state variance. So the steady state oscillations about the consensus point. Here you want to make the dynamics as fast as possible. And you can formulate the problem the same way by defining the convergence rate as essentially the maximum absolute value of the eigenvalues of the system, which you can also compute for this simple case in closed form. Sorry, not in closed form, but you can compute through those characteristic polynomials. And the same thing can be observed in this case. So we try, just for comparison, both uniform gains. So that's where you just compute K as one scalar times the Laplacian matrix of the graph. This is a simple way to achieve consensus by, let's say, construction. So we try both to optimize that single scalar G gain, which is essentially applied to all links, and also to let K an arbitrary symmetric matrix with let's say the correct structure to achieve consensus, just like the previous case. And you see that the same behavior essentially can be observed also to optimize for the convergence speed, so the convergence rate. And here I plotted the curves for delays that grow linearly and quadratically with the number of interconnections. And you see you have different behaviors. So again, so in the second case where delays increase, let's say, faster, so you penalize in a sense when you add interconnections because they increase the delay in the feedback. The optimal networks are very sparse. I think they're so in let's say the optimal case where you have all different gains, the optimal architecture is 2, but for a single gain, you even have nearest neighbor topology is the best in this case. Here, it's a bit of a mix, but still you see that in general, sparse interconnections are good or best in terms, or optimal in terms of performance. Okay, so I'm not sure before I start with the second part, if you have any questions at this point. So next I'm gonna switch topic slightly. So if you have any questions, just ask. Otherwise, I'll go ahead.
So you're looking at consensus dynamics. How universal is that?
This is a good question, actually. Here we only made the case for consensus dynamics. So consensus, I mean, I was probably the consensus, let's say, thing here is not fundamental, meaning that what we did here essentially was studying, in this case, single integrator dynamics, essentially. And to get to consensus, you need to enforce some structure on K, which is like Laplacian-like, for example. I'm not sure that is super relevant, although I didn't investigate more general dynamics. I would probably say that here, the, let's say, crucial part is that you are, let's say, you're optimizing for some gains that get you to a steady state. So here the steady state corresponds to a consensus, but it probably need not be. For sure, for this, let's say, for the study we did, so for both this case and the stochastic dynamics, the, let's say, linear dynamics, there, that is probably the, let's say, the aspect we exploited the most for, you know, for the structure of the problem and of the dynamics. So that is probably playing a big role in, let's say, extending or non-extending these findings to other to more general models. I don't think the consensus specifically is that crucial, but again, I haven't investigated that yet. Yeah. Does the language answer the question? No? Okay. Thank you. Okay. Yeah, so I feel this, let's say, gives I mean, so of course, a small step in a sense, but somehow I believe it's nice. Then you get some, somehow you challenge a bit the some standard assumptions that are made in the literature. So this hopefully may shed some more light into some more, let's say, realistic implementations of distributed controllers. Okay, so I'll now switch to spatially invariant systems. So spatially invariant systems are, so in the context of multi-agent systems, actually are, let's say, they are, of course, an abstraction, but just to, let's say, connect a bit more concretely with what I'll be talking about in just a few minutes. Let me bring up these two other examples of multi-agent systems. So you might notice that in both cases, the system essentially lives on a kind of string, 1D, let's say, domain, very in a very abstract way, of course, but both platoons and also soft robots of this kind, at least, you see you have all controllers and actuators. Subsystems are essentially dispatched on a line. And this this gives me some good, let's say, motivation for this setup of spatially invariant systems I'll be considering. I should mention that actually these systems are quite broad. Let's say, I mean, they are quite a broad model. You can use them to model even other more let's say, less structured interconnections and multi-agent systems. But for the sake of what I'll be presenting, I'll be mostly sticking to this kind of dynamics on, let's say, the real line to stick to the model. So spatially invariant systems are this kind of dynamics where you have some symmetry with respect to the spatial dimension. So let's say the dynamics is invariant with respect to spatial translation. And this is, I would say, equivalent in a sense to time invariance. So, but projected on some spatial dimension. So you can imagine if you, let's say, apply the dynamics and then you shift the system, you keep seeing the same effect as if you would first shift the system and then apply one step or one iteration, whatever, of the dynamics. So the very general model for these systems is that one where your state psi is, generally speaking, a function on the real line, say, and A there is an operator that has this property of spatial or translation invariance, which from which the let's say the name, the concept of spatially invariant systems. So let me give you a couple of examples to make this a bit more concrete. One, let's say, very simple example is reaction diffusion processes over the real line, again, in this case. So here, this is just a simple process, for example, the heat equation with some damping. So where phi of x is a function of the real line that evolves according to this equation. So for example, those three bell-shaped curves could be some different snapshots of these dynamics. Other cases are maybe a simpler one are circulant multi-region systems. So again, multi-region systems with ring topology or circulant topology. So you have the ring topology and then multiple interconnections, so connecting to neighbors of neighbors and so on. Just a simple vector dynamics where A is a symmetric circular matrix. And this is another kind of multi-region system where in this case psi, so we're not on the real line, we're on the integers, for example, or integers modulo some natural number. So one very interesting thing that motivated actually the study of these systems since the beginning of the 2000s was that if you wanna find the optimal controller for this kind of systems, where optimal controller here is the H2 optimal controller, so let's say the standard notion of optimal controller. The optimal controller has this, let's say, inherent localization property. What does this mean? It means that, so let's take this example to make it easier. The optimal controller is a spatial convolution with the state, where this k-opt is the convolutional kernel. And the convolutional kernel, in this case, at least, it's something like that. So it decreases very fast with space. Actually, it decreases asymptotically exponentially across space, which is typically referred to as this inherent localization. And you see that this motivates, for example, implementation of distributed controllers with these systems, because what this kernel is essentially saying is that if you go, say, farther away than 4 space units from where you're at, all measurements coming from farther than that, they are essentially useless because they are amplified by very small numbers by the convolutional kernel. So this means that, for example, if you have a platoon here and each of these sticks represents a truck, then that is gathering information from the neighbors, then you might only want to care about who the first, the truck that's closest to you, and then the one after, and then you don't need to care anymore about the others. So this is nice because, of course, you can implement distributed controllers. Well, heuristically speaking, you can implement distributed controllers by truncating that kernel. So zeroing out what is farther away than whatever you decide based on, for example, some bounds on the performance loss or not. So that's one way you can implement a distributed controller from the optimal controller, which is, of course, usually centralized, or let's say in this case would necessitate to measure the whole real line, for example. But it's after 4, let's say, is negligible. So this is the standard scenario. But what happens when you have some communication delays? This again is, let's say, non-trivial. And we consider the same model. So when your control inputs are computed with state feedback, but with some communication delays, let's say that here are again reflected into feedback delays. So it's, let's say, in broadly speaking, it's non-trivial how that convolutional kernel you saw before would change in this case. And if this would affect the truncation, because, for example, you might need to truncate farther away in space or not. And depending on this understanding, your, let's say, the naive, let's say, distributed controller computed from the nominal scenario might be very different. For example, you might need to acquire measurements from 2 tracks farther away in your platoon, ahead and behind, for example. Okay, so just to give you a, Giacomo, I'm not sure about if we should care about that. Okay, just to give you a glimpse at how we solve this problem. This is a, let's say, a standard way to solve this kind of problem. So I'm not taking that much credit about that, but I'm going to show you because I believe it's interesting. So the spatially invariant systems have this very nice property that if you apply the Fourier transform, that will be that calligraphic F, you, so to say, diagonalize the system in the so-called spatial frequency domain. And again, this is the same thing, let's say, when you apply the Fourier transform to a time invariant system. So what you get is you get a family of decoupled systems in where that lambda there represents spatial frequency. So if you, so for example, if the state is a scalar function, here you have a family, an infinite family in general, but still a family of independent systems, of independent scalar systems. So that, of course, makes analysis and design much easier. And that is the principle that has been used in the past to derive, for example, the property of localization of the optimal controller. For the reaction diffusion process, just to show you some example, this looks like that, where lambda is a real variable. And this means that you actually can also decouple the optimal control problem. Essentially, you can decouple it into solving a family of independent optimal control problems. So this is what we did. And for us, it means essentially to compute that K, that's the optimal, let's say, gain at the spatial frequency lambda with some delay K, some delay T. And we consider this problem. So minimizing the H2 norm of the system subject to stability conditions, of course. And it turns out that, so you're going to compute this guy this way, where H there is a transfer function. And I'll show you in the next slide, stability conditions can also be computed in closed form, and they are a box condition, essentially with respect to the gain K. This is interesting for delay systems, because if you don't have delay, here you just have plus infinity. So there's quite a difference if you actually account for delays or not. Because if you account for delays, here you have a constraint you don't have if you don't account for delays, essentially. So it turns out you can compute this H2 norm by computing that integral in closed form. This is the same paper I quoted before. So that's actually the same result, but with the additional complication in a sense that A here is no zero. In the previous case, it was 0. So this same expression was much more simple. And this looks like this. So you still have, you see these curves that gets narrower and raised in a sense as you increase the value of A. So, and of course, as A becomes from, let's say, negative to positive, so the systems, the unforced system becomes unstable, here the domain, let's say, of the gain, of the feedback gain you need to supply becomes strictly positive. So you need to actually enforce some feedback control to make the system stable. This is quite intuitive, but then also this shape of the curves is interesting to study, considering delays. And here again, this is the difference between non-zero case, zero delays and non-zero delays, you see that the stability region for a problem changes quite a lot, and also the optimality region, which is the darker here, you see it changes quite a lot. And very interesting, actually, in that case, it turns out the optimal gain goes to zero as A goes to minus infinity, regardless of the weights in the optimal control problem. And this is interesting because the problem is always well posed, and that is always the case. For the standard optimal control problem, this is not the case because the problem is ill posed if R, so the penalization on the control goes to zero. So the optimal gain might be arbitrarily large. And okay, so it turns out that in the limit for the expensive control case, you can compute the optimal controller, let's say the asymptotic optimal controller in closed form. I don't want to indulge too much on this, but then this is to show you that you can retrieve the optimal controller the same way. So the optimal controller is again a spatial convolution with the delayed version of the state, so delayed measurements of the state. And the interesting thing to notice here is that the convolutional kernel is itself a convolution. So it embeds effects of both the optimal controller in the delay-free case, and also a filter, let's say, that accounts for the fact that you are using delayed information. And this filter actually goes to zero as the delay increases. So this, again, is telling me that if delays are super long, then essentially feedback control is useless because you cannot decrease the cost by any means. And this is how it looks like. So for the reaction diffusion process, so the blue curve here with the pointy curve is the kernel without delays. And you see that if you have delays, you have a much, let's say, flatter curve. And you can also somehow quantify where the two kernels get more or less the same. They are asymptotically the same, actually. But here you see around the origin, there's a huge gap. And that depends on the coefficients of the system, in particular of the delays. Depends on the delays. So to mention the effects about truncation, and then after this, I'll be done. What does this mean with respect to distributed control implementation? So I mentioned at the beginning of this part that the localized structure of optimal controllers for spatially invariant systems is useful because it can be used to implement somehow easily a distributed controller by simply truncating the convolutional kernel. But if you consider the count of delays, this truncation requires adjustments because, so in this case, so you see that I've plotted two vertical lines here. The dashed line tells you where to truncate if you don't have delays. And the solid line tells you where to truncate if you do have delays. So you see that in this case, the effect of delays is essentially negligible on truncation because to account for delays, you need to truncate closer to yourself compared to truncating without delays, but for the optimal controller. So in this case, so for a small delay, 0.1, delays are negligible, essentially. But if delays increase to 0.5, in this case, you see that the solid lines that tells you where to truncate, if you also want to account for delayed information, this is farther away than the dashed line that tells you where to truncate in the absence of delays. So what does this mean? It means that if you didn't think about delays and if you truncate based on the optimal controller without delays, then you're losing information that is actually important to when in the actual performance of the controller when it's fed with delayed information. So in this case, with delay 0.5, you are actually, if the gap between these two lines will also decrease performance and potentially leading to instability of the system if this gap becomes too large. If you don't account for delays when computing the optimal controller and then truncating the kernel to implement a localized distributed controller. I'm not sure this concept is clear. If not, just ask. But so this is, let's say, one of the main, let's say, side effects of our analysis on this kind of system. So again, it's interesting because it shows you how exactly, let's say, quantifying or anyway accounting for non-idealities such as communication delays in this case can really change the implementation of your of the distributed controller on the real system.
So look, I'm not sure I understand.
Yeah.
This is what you're showing, or this is something different. But often I don't know the delay, right? So if you compute for the optimal control for a nominal delay, do you have guarantees, theoretical guarantees on how that optimal control behaves in a range of delays? Is this related to that? No, this is not answering.
So this is not answering the question, but I will still say if you do have some nominal delay, and then for example, that you also have some bounds on the delay, for example, so you have a nominal and some confidence bound, for example, then I would say you can actually use this kind of analysis to answer your question, because say you have some nominal delay, but you also have some bound, and so the nominal delay, for example, is this, but then in the worst case, for example, the delay could be as much as this one. Then in this case, for example, this controller will not guarantee the same performance as the same controller with 5 times the delay, for example. So you can somehow, I would say, you can quantify that by computing the controllers and just opposing these vertical lines accordingly. You can get a sense of if you're losing performance, for example, of how much information you need to embed in the control inputs calculation. Then all of this was done with, so these plots are done with are obtained with by let's say computing the controllers and these lines with a given value of t. So they don't account for uncertainty, for example. But so again, I would say one, let's say first assessment you can make is to, for example, trying different values, or if you have a range, considering the upper lower bounds, and then computing the controllers and where you would truncate for each case, and comparing that to the nominal scenario, for example. Does it make sense? Thanks. Okay, so actually this ends my presentation. So just to wrap up quickly, today I've presented to you these two different approaches of addressing communication delays in information exchange of distributed control systems, and in particular, first looking into the optimal communication topology, so controller architecture, where you have communication delays that change with the number of links. And then for spatial invariant systems, looking at this convolutional kernel of the optimal controller and how it relates to delays, and how you will need to truncate it, for example, if you want to implement a distributed controller. There are actually a lot of say questions, other directions you could take from here, such as also what discussed with Giacomo right before, but also so other control settings as well, like robust control and nonlinear dynamics. And then on the other hand, considering broader communication constraints and more realistic, for example, or more complex communication structures. So spatial locality, time varying network, time varying delays, those are spatially varying delays. Those are also somehow important in some contexts, and so on and so forth. Okay, so this ends my presentation. Thanks a lot. And if you have any other question, I'll be happy to answer.
Any questions also from people from home?
Luca.
Yep.
Sorry, probably I didn't pay enough attention to your initial part of the presentation, but can you say it again, how the delay in your models depend on the topology? It depends on the number of links, or on the degree of the.
Yeah,
I didn't understand. If it is constant all over the graph, or it depends on the node?
Yeah, so let me go back to the model actually. Actually, let me go back to these couple of plots. I think they are it's a bit easier to understand. But
Yeah,
so correct. You're correct when you say that the model we use, delays are let's say constant across the graph. So on each link, we assumed the same delay. So these are, let's say, a fixed parameter given a certain topology of the communication graph. So if you look at this equation, for example, these models the evolution of the whole graph across the whole graph, and you see here the delay tau n. This is so this depends on n, which let's say accounts for how many links you have, but then this tau n is the same across all links. So each link incurs this same delay. And then if you have different architectures, so if you shift, for example, from this to this, then on each link, the delay increases or decreases, for example. And so to answer to actually answer your first question, for the case of so we first studied, which are a bit easier to study, circulant graphs. So exactly this kind of graphs I'm showing. In this case, n would be the number of neighbor pairs each agent has. So in this example, n would be 2, and in this case, n would be 1. But then, of course, this is just I mean, you could do the same by considering the amount of neighbors. In this case, of course, this just doubles the delay, so it's not really relevant. And then we did the same thing for general undirected networks. So in this case, for example, so in this case, n is, let's say, the number of hops. Number of hops mean that you are connecting. As you increase n, you are connecting directly each node with neighbors one step ahead, one step further. So in the case of generic undirected networks, we use this model as n is the number of hops. So for example, n equal to 1 means you have the plane network and each agent only exchange information with the nearest neighbors. If you n equals to 2, means that you connect each node with neighbors of neighbors, and so you have more non-zero elements in the feedback gain matrix, and so on and so forth. This is, of course, the model we use, so it's not, let's say, very, it need not be a very precise model, but I would say, let's say, the main effect we wanted to mimic is this increase of delays as your architecture gets denser. So, so that was the aim.
Okay. So even if a graph has a lots of neighbors, if a node has a lots of neighbors, of a node has just one neighbor, it will increase. You assume that it will increase in the same time delay.
Yeah. Yes.
Because I mean, you have heterogeneity in this graph that is at your shoulders, and as you are looking, that I'm looking,
Yeah.
and so, for example, a node of degree 4 and a node of degree 2 will exhibit the same time delay in your model.
Yeah, yeah. Then yes. So in this case, yes. Then I let's say on the one hand, we tried, let's say, to so growing the network with number of hops. Let's say rather than growing by adding links arbitrarily, we tried to do this to somehow, I wouldn't say make the network homogeneous, but let's say to not make it too heterogeneous. So as you're saying, then on the other hand, also of course depends on the communication model. For some communication models or protocols, let's say a single delay parameter could be, let's say could make sense. For other protocols, so for example, time slotted protocols, then of course having so one node that only has one neighbor and another node that has 10 neighbors, of course, in that case, the delays one would have to consider different delays. Then the let's say main reason we were refrained by to add this complexity to the model is that computing the cost functions and the optimal control in that case becomes very, very challenging. Usually you just have non-convex problems. So we wanted to stick to, let's say, a bit simpler but more tractable formulations to get a more, like a deeper understanding. For general communication models, I agree that you would need to have, you will need to account for multiple delays, broadly speaking.
Okay, thanks.
Yeah, thank you, Fabio.
Any other questions? Okay, I can ask one last one.
Of course.
From what I remember from spatially invariant systems control, then there is a role of the dimension, right, in determining what is their performance limitation. Right, the spatial invariant systems on the circle have certain properties. Those that are spatially invariant on the toes have some other. And do you get a dimension-dependent effect also in your trade-offs?
So actually,
trade-offs that you're looking at.
So we only for this study we only studied the evolution on the real line, essentially. So, or in fact, we studied the case where your spatial frequency decoupling gets you to the spatial frequency parameter on the real line. So we didn't compare with different spatial dimensions. So I couldn't actually answer your question as of now. I would expect you do have some dependency on the spatial dimension as well in this case. Yeah.
Well, let's thank Luca then, and we close the public session.